Okay, so hello everyone. Today is the 16th of December 2024, and today we're very happy to have Matteo Campanelli, a ZK, non-ZK researcher at Off-Chain Labs, working with a lot of ZK and non-ZK topics. And yeah, this is a paper co-authored with Mathias-Hall Andersen, and Matteo, the floor is yours.
All right, Misha, thanks for the introduction, and thanks everybody for being here. Yes, so the topic of this work is SNARKs for integers. It's not something we hear so much about. And the work is from this recent ePrint called Fully Succinct Arguments over the Integers from First Principles, which is with Matthias. And let's see, let me see if this works. Okay, looks like we get transition. So I'm going to assume that you know lots of stuff, but if I assume too much, or if I confuse you, just raise a hand, try to get my attention. And I can see some faces over here, but who knows? So, okay, the setting is, of course, that of SNARKs. We have a certain relation, an NP relation of cert, and we have a prover who knows a witness and wants to prove, given a very compact pi, to the verifier that they know this witness. So, for example, there could be a public input here. So there's an example on the left. The verifier just holds some hash, and the prover actually knows a pre-image of the hash, a graph, and he knows some complicated witness, for example, a 3-coloring for the graph. And the type of security we want to regarding SNARKs is usually modeled through extractability. There's SNARKs for a reason, arguments of knowledge, which basically means that the prover knows the thing. I'm not going to get into how we define it. I'm assume you know, and if I hope it's not going to affect your appreciation of the presentation otherwise. And then, of course, the other thing we want, another thing that we want is succinctness. So this proof should be significantly smaller than the actual witness size. Nice. And we're living in a very nice present in this sense. So we've seen efficient SNARKs for many computations. And when I say efficient, I mean concretely efficient, so they're practical, and also through a wide variety of metrics. So very classical example is growth 16, that basically with a couple exceptions represents the state of the art in terms of proof size, right? So basically 3 group elements, and the verifier is also very efficient. So in 4 milliseconds, and I don't know, standard machine, maybe anybody please correct me otherwise, but half a second on the standard machine to prove a SHA-256, you can get your proof. But that's not the end of the line. I mean, we have this incredible explosion. This is just a very partial list of lots of work schemes with different trade-offs, right? So we could achieve even better proving time and such and such and such. And there's really an embarrassment of the riches here. Great. Now, I think the angle of this presentation is this, that there's a caveat. It's not a strong caveat in a sense, but it is a caveat that good efficiency really comes from good representation. What do I mean here? I mean, many of these works, and there are very few exceptions, but in many of these settings, we're talking about finite fields of prime order. So basically, we need to be able to represent our computation into, say, an arithmetic circuit over here on the top, or an R1CS or something else. Of course, these are not the only ways we could arithmetize that. And in case in point, we actually don't, we move beyond these two representations. We have lookup arguments, specialized gates, because representation is important. But that aside, so we have these hammers that are able to basically, hit finite field of prime order nails, and so everything should be of the type for it to work, right? And it works pretty well. Here, I mean that in a good way, because anything that we can reduce to that works. And we are able to reduce lots of things to that. The problem is when it's hard to do that, when we have certain computations that do not seem to admit easy representations or finite fields, right? An easy example in such sense is RSA signature verification. So I'm going to open that box in a second a little more, but here, so given, for example, a public key, for example, given by big N, product of 2 large primes, a message M and a sigma, what we do is we check an exponentiation of the signature to some public exponent. The exponent is usually either 3 or 2 to the 16 plus 1. And we check that equals the message mod n. This is not exactly what happens. It's really the hash of the message, but that's nothing changes much here. And of course, there's more in the RSA world that falls under the category. There's a bunch of works on set membership that try to efficiently represent RSA accumulators. There is cryptography over rings, so not finite fields. And then we could look at, I'm going to open these other boxes too later, but I want to suggest that there are other fields, types of statements that don't quite fit the finite field category. Scientific and number theoretic statements, mathematics, machine learning, we'll open the box a little bit also. Cool. So, and a common thread here I want to suggest is that there are integers underlined. I think I'm gonna showcase that a little bit, but if one had a proof system natively works over integers, we could sort of tackle this niche. It's not, or tackle these gaps. I'm not sure they're so niche really. Okay, and just to double click on the cost of emulating integer computations, I want to just open the box of RSA signature a little bit more. So this is the setting we just saw. So what we usually do when we have a finite field, SNARK for finite fields, and we apply that to some type of computation, is that we emulate in the finite field lots of things, right? So if we're doing integer addition or addition modulo stuff, I could, for example, break my big integer or my big group element into limbs, chunks, and then emulate chunk-wise arithmetic in some way. So let's look a little bit at what happens, right? So for example, you can see this is a very simple statement over the integers, right? So let's use the definition we know of basically modular arithmetic. And this statement reduces to I know quotient, an integer, such that qn plus m equals this thing. I'm just using the definition of mod n here, right? And so I just need to show, as a prover, I just need to show you a Q, and then I just need to, the circuit corresponds to this line plus the exponentiation sigma to the E. And E is this thing on the right. And so let's make this exercise. How big is the corresponding circuit, right? So as a Z circuit, when you have integer gates of certain, there's a finite field circuit. So, okay, as a Z circuit, it's pretty simple. It's 16 constraints. You can convince yourself with pen and paper, but the number 16 roughly comes from the 2 to the 16 plus 1. You need some care to get exactly 16, but you can get it. Now, I'd like to pause for 3 seconds. Maybe you already know the answer, but make a guess in your head of how many gates this is going to correspond to, how many multiplicative constraints. In the case of F circuit, where F for us is, say, the scalar field of BLS 12381. Okay? Okay, if you're ready with the guess, I mean, this is the real answer. It's 90K constraints, and it's not even, it's not a straw man. This is true. If you look at XJ-SNARK, one of the papers that looks at basically heavy tooling for automatizing, like how to translate a certain relation to a bunch of constraints. So this is a state-of-the-art compiler, and this is what gives us. Okay, maybe there are small improvements of what can do, but this is significant. And so one way of looking at this, it's a little inaccurate, but it's suggestive in a meaningful sense, is that if I have a proof system that natively works over the integers, it needs to be 5,000 times worse than SNARK over finite fields to be, for me to be worse off. Now, this is not perfectly accurate because this is not perfectly apple to apples. The 90K constraints, for example, is also taking care of the size of each integer, right? So, but as later we're going to see, there is a meaningful technical sense in which sometimes, for example, in our protocol, there's a part of the protocol where you only pay in the number 16. 90K never shows up. Yeah, the size of the integers never shows up. So this is to suggest that efficiency-wise, there's something that's going on that we can optimize. But there are other reasons also. So Beyond efficiency, if we had native SNARKs for integers, this will lead to safer, simpler circuits and happier developers. So, for example, an obvious implication is this. So there's no need for developers to write or handle large complex circuits if they're writable as simple ones, right? And then, like somebody could sort of respond to this and say, but we could just have a compiler to it. I mean, I just showed you a compiler, right? Fine, of course, but then somebody needs to have the time and the resources to design, write, document, and maintain the compiler. The XJ SNARK compiler is great. Maybe it's not the end of the line, and maybe I actually don't know how much documentation there is besides the paper. Maybe I'd be happy to be proven wrong. And then, of course, fine. Maybe you could say, yeah, we have all the money in the world. We don't mind the additional complexity and more layers of indirection. So it's fine if you have all these tools and somebody learns them and teaches them. Also, it doesn't matter if they're specific to certain parameters, because of course it's really hard to have very general compilers, right, for any setting with any. So we believe these parameters will never change. It's fine. So we're good. Don't worry about this stuff. Okay, but there seems to be a bug in your circuit. Good luck with debugging the 90K constraints, right? So you still need to look at the thing and start dealing with it, and so on and so forth. So I don't. This is tongue in cheek, of course, but is to say I'm personally a skeptic. I'm skeptical about the fact that we can automatize anything. I think simplicity is very important, and then we shouldn't ignore that. And this is even besides efficiency, right? So there's an argument there, I think. That said, so hopefully I'm motivated. I'm going to keep motivating this in a sec, but I can start hinting to what we're doing. And what we're doing is succinct non-interactive arguments that work natively over Z. This is the goal of this work. And by natively, I mean that basically Z arithmetic and integers are a first-class citizen, and they introduce as little overhead as possible, in big terms. And succinctness, you should think in the usual sense, but also something extra, and then I'm going to talk about that later. Also, what do? We have both concrete constructions, but most importantly, we had lots of fun doing that. That was our starting point. We start thinking in general about this. So we don't just want to give a construction and then run away. So we want to have, we have all these constructions from SNARKs, the big cloud I showed you earlier. What are we going to do? Are we going to just start over and start thinking about SNARKs over Z? No, we were looking for a framework where we could plug in things from the past and future and so on and so forth and get more constructions. So those are our goal. But then I want to keep boring you with motivation, because I think it's very important to get the whole picture. It's not just it's not just a cute thing here. So as I try to suggest so far, I think so. What I'm calling SNARKs for Z. I mean, they have this potential, right? So some problems become easier, some things become simpler. You can get from 90K to 16 constraints, and maybe you have a system that's going to get you fast enough there. Also, you don't need to write those 90K constraints or use a compiler for that. Just write the very, very intuitive 16 constraints that you can come up on paper right now. And then there are other things. Once you start having these tools, you can start looking at how to approach problems differently. Cool. So what are examples of that? Well, for example, you may know this trick already, but range proofs over the integers get pretty cool. So you can make a range proof for any range in 4 constraints. And what you use here is the sum of 4 squares theorem, which basically says that if you have an integer, this is non-negative if and only if there exists 4 integers such that you can square them, take their sum, and give you the integer, right? That's on the top. And you can apply this trick to basically give you an arbitrary range proof. So you can, below you can see basically some intuitive ways of proving a range proving that n is between low and high. All right, and now of course it doesn't mean that you're not paying some other things, right? But then this is pretty simple. Maybe the trade-offs appear. It's too early to say. It really depends on the system. Once you have SNARKs for the integers, you also have SNARKs for Q. This is sort of an intellectual musing to some extent, but not only. I'll get to that in a second. Once you have arithmetic over Z, you also have somehow arithmetic over pairs of integers. So just as an example, imagine a multiplication gates over fractions will look like this. You just check the obvious thing. Just check numerator, denominator constraints. Addition is similar. And of course, since these are irrational numbers, the denominator, at least in the input wires, you need to check that the input wires have non-zero denominators. And then once in a while later in the internal wires, you may want to check that. And the way you do this, we're working on a next draft of the paper where we describe this, but you adapt basically some of the ideas here. It's just a variant of this. 4 or 5 constraints you can do. Okay. And once you have SNARKs for Q or something similar, well, you start being able to talk about, decimal numbers. Now, you're dividing a large number A by large number B. Okay, now you have the fraction. And then you do something else with it. You're handling, all the decimals the whole time through fractions if you want. This is not necessarily the most efficient way all the time, but sometimes you need all the precision, and sometimes it can be giving you trade-offs. In scientific engineering, computations of sorts, simulations in physics and such, this could be handy. And in math, but in math more than arbitrary precision, floating point, decimal numbers, arithmetic is more. I'm more thinking of number theoretic stuff. Cool. And then, maybe more interesting, I stumbled upon this recently. So I wonder what it can do for machine learning. So one of the challenges for machine learning is usually floating point arithmetic. It's a little bit of a pain in the neck. And I can see this helping in 2 ways. So first, in a direct way. So there's this new paper by Liu and Sun 24. It's an archive. Addition is all you need for energy-efficient language models, where the authors make the claim that if you only have integer operations, you're basically not losing so much precision. They show a way of making it work without losing precision that would affect the performance of your system. Well, since we're talking about SNARKs for the integers, you can see where this is going. But also, some of the techniques I just showed you maybe can be used in a sort of indirect manner. I don't know, arbitrary precision seems too much for machine learning, but I'm not an expert on that, so maybe one could use that. Or one could come up with new ways to hybridize what I just showed you to achieve floating point arithmetic. Fine. Enough motivation. It was just to inspire you a little bit, but I'm going to try and tell you about this work. But first, I need to give you a note on what we mean by succinctness. And then, of course, I want to say one thing about prior work. If you have any questions, maybe we can take some quick questions real quick, if you'd like. Cool.
I might add another question, but I might add a comment that I wanted to say. Also, okay, I also remember there is this type of FHE scheme, right? Wouldn't be able to tell you exactly the name of the direction, but it's one of these 3 directions. And there's an FHE scheme that actually strongly relies on arbitrary precision floats. So there are like 2 families that do it over, I think, over the integers, and there's the third one that does floats, which I think might be a good example to one of your previous slides. Maybe I can try to find a paper and send it to you after I talk.
Yeah, that'd be great, because it's something I haven't looked at much yet.
Yeah.
So yeah, I'd be grateful. Thanks. Okay, so before we get into the weeds of things, I just want to make a point about succinctness. There's something funky going on, but very natural, really, that goes on with succinctness when you look at integers. So let's think of what we think about when we think of succinctness. You have a circuit or something similar and a witness. A witness is a vector of elements. And these elements are scalars, which means they're all of the same size. They're all lambda bits for something like that. And so what we say, a proof system is succinct if, as a necessary condition, we require the proof to be small, so it should be sublinear in the number of elements. And then sometimes we require the verifier time to also be sublinear, right? So that's a small o, by the way. But over Z, something funky happens. So take this absurd example. So take a witness with 1, 2, 3 elements, right? N equals 3. But these are gigantic numbers. So for any practical definitions of gigantic, right? So to the 60-ish numbers, 50 factorial, which I think is of the same order, and take one of the largest Mersenne primes, and then here you go. So, like the number of elements is very small. So the traditional, even if you achieve the traditional form of succinctness, you're not getting much here. This is an extreme example, but this is what happens over the integer. So anything in the spectrum is going to happen, right? So the norm of the witness is huge. Number of bits representing the max among the integers is very large. So in this paper, we want to sort of initiate the study of this explicitly. We want succinctness in both the number of elements and the norm. And we call this full succinctness. Okay, so real quick, prior work. Since I talked about going beyond finite fields, it's very reasonable to look at what people try to do over, for example, rings. So there's a line of work, Rinocchio's paper by Chaya, Anca, and Eduardo Soria-Vázquez. That, I mean, here, the stuff on the right, they're more like notes. They're not necessarily limitations or bad points. Sometimes there are ways to compare to our paper simply. But so limitations of these, for example, are that this work is the ZNA verifier. And Chaya, Anca, and Eduardo use sort of variants of knowledge of exponent assumptions, right? And so over rings. I say here relatively unstudied. I would lie if I said that we have lots of analysis of knowledge of exponent assumptions over elliptic curves, say. But these are really, we don't know what the intuitions are about this, as far as I understand. And then we have a very nice work by Eduardo, which was published in TCC 22, which you can interpret as GKR for infinite non-commutative rings. I forget the actual title of the paper, but I chose that summary because it was more impactful, but it's very close to that. And here, the limitation of this work is that it looks only at deterministic computation, right? Which is a little bit of a bummer in many situations. But the cool thing about this work is that it's the cool thing, but also limitation at the same time, is that it goes way beyond Z. So it looks at infinite rings in general, even without requiring commutativity. And what's interesting about this work is that Eduardo is looking at all these techniques that we normally use and pushing them to the extreme, I recommend within this paper. But in a sense, the generality that's achieved here is not very helpful for us. And then the most okay, go ahead, Misha.
Yeah, sorry, just wanted to I guess it's also taking another question, but could you confirm that GTR is this sound check protocol?
Yes, it's basically take a circuit and go depth layer by layer using the sound check protocol. Yes.
Okay.
Sound check protocol is the overwhelming majority of what you're doing there. Yes.
Okay, so it's a kind of a way to build NISICs, because I think the sound check protocol is a term I knew for quite some time, but the abbreviation started popping up in my area, like in my mental space just recently. So it's the whole NISIC with the
yes,
with the sound check.
Yeah, it's the key. The key tool is definitely the sound check. You're right, but then you apply that. Say, an important contribution of GKR in the line of work is that it applies it to a circuit. So arithmetizes each layer of the circuit and sort of the space between them in a way so that you can use the subject. So that's also
okay, makes sense. Thank you.
So I think the most important work to mention for this work is probably Asiacrypt 2020 by Towa and Vergnaud, succinct Diophantine satisfiability arguments, which is quite close in scope and Ingalls Tower work. You can think of this as, it's just my own paraphrases of it. I think it's limiting to call it this way, but you can think of it as to give some intuitions as a bulletproof over the integers that tries and use integer commitment. So you, for example, see groups of unknown order techniques, which is also what you're going to find in some parts of our work. So a few things to say is that this work is not fully succinct. So the proof is log in the number of elements of the witnesses you expect in bulletproofs, but you also see you have a number of bits that's linear in the norm. So if you have a large integer, you're going to have a proof that's linear in that. And the verifier, of course, being a bulletproof flavor scheme, is linear in everything. Is not. Oops. Sorry. Yes. And okay. And interestingly, though, so this paper, compared to ours, it does have zero knowledge. We don't treat zero knowledge at all in this work, and it has what I'm calling here a restrictive form of zero knowledge. This is no Bayanese. Thanks for coming. So it has a restrictive form of zero knowledge. I don't mean that in a bad way. It sort of inherits. This restriction is inherited from the fact that this work is not fully succinct. What do I mean here? So in this work, what happens is that you're leaking the number of elements of basically of the norm of the witness. And this is unsurprising because the proof does that. So what I'm trying to point out here is not something about Towa and Vergnaud, rather is about what does it mean to be zero knowledge when it's about integers. And one thing you want to do is, for example, to strengthen this notion, to look at the relation properly and then define it in a way that doesn't leak them. Okay, so to summarize, I'm sorry this was pretty long. So there's no full succinctness in this work. The verifier is not succinct either, it's linear, but it achieves zero knowledge. And zero knowledge, if you want to think more about that, there's this interesting caveat. Okay, one thing about these works is also that they take, to some extent, certain specific schemes and adapt them. And so our goal is the general treatment, and so none of this works. Cool. So in a single slide, what do we do here? We propose a bunch of techniques and framework for fully succinct SNARKs. So the idea is that this is sort of a factory. You have some previous SNARK techniques, and they satisfy some very simple property. You plug them in, and here you go, you get a SNARK for integer. I'm going to explain a little bit more about how that works, and then we show how to instantiate this framework and so on and so forth, and then we obtain one concrete construction, which is really few variants of the same construction. Zaratan, Spartan for, you can think of that as a Spartan over the integers. And here, just for context, so where's this coming from? Zaratan is a fictional creature from the work of Jorge Luis Borges, but also, as far as I learned, from Arabic folklore. It's supposed to be this giant turtle that looks like an island in the sea, but here I imagine that there's something that's sustaining the flat earth of the infinite integers. Anyways, so let me say something about the efficiency of Zaratan. So we got, let's remember, we got a witness, and the witness is a vector of integers, of n, size n. And let's call m the maximum size in bits of each wi. So this is the largest, take the largest integer, there m is the number of bits used to represent it. And so if you think of what does it mean, what's the size of this computation, right? It's n times m. You have n things of size m each, right? So if you have something n times m, that's linear. Cool. So here's the table. There are two versions of Zaratan, really. So a fully succinct version, which works with different trade-offs in different regimes. So the full succinct version is always the same, and there are big O hidden here. So this is, for example, the proof size and also roughly the verifier time is logarithmic in the number in the norm and log squared in the number of elements. And then you get linear proving time for computations where, so what is fraction here, for some computations. So the top row means roughly that, here's a way to interpret that the size of each integer is not too large compared to the number of elements. That's just a way of interpreting it. However, you could also have, for any computation, you get the same proof size, and you get something that's almost linear, really. So it's not linear technically in any technical sense. I'm calling it linear minus minus. But it's basically linear, linear, linear in the overwhelming majority of the protocol. And then there is one step in one sub-protocol in one of the two core components of Zaratan, which requires m squared bit operation. So m is the norm, not the number of elements, by the way. So it's unclear how it's going to impact things. That it might in certain setting, definitely, but this is not technically linear. And then if you want to give up full succinctness, right, and you want to pay, say, additional proof size if the norm is not very large, then for any computation you can get linear. Because the expensive step, or the expensive step you have here on the right, is only for full succinctness. Yes.
I'm sorry, by approximate m, you mean approximate log m, or?
Yeah.
Okay.
No, I'm sorry. What was it? I didn't understand. I was nodding you to keep going. Yes.
On the bottom table, you say above plus approximate m.
Yes, proofs whatever elements you have above plus m, and of course the m dominates log m, but
okay. So m is already logarithm. So m is the max size of the. So m is the maximum bit size of any single integer used in the computation. Okay. So logarithm square of m is really good. Log m. Okay, on top. I see. Okay. And also, I guess the fact that your proof size, it depends on the maximum integer size, kind of creates a problem for zero knowledge, right? So you would need to, like, your design inherently reveals how big are the numbers that you're working with. So you would need to cap that somehow.
Correct. Yes.
Okay.
Okay. So this is the one construction at a glance. And for the rest of this presentation, we'll really talk about how we get there and what else is left. So the turtle is just a small part of the thing, as far as I'm concerned. Okay, so I promised this general treatment, right, and general techniques. And there's one core technique we identify, and it's called fingerprinting. Really, there are many intuitions on the same thing, but you're going to find in certain literature this technique called fingerprinting. But it's a type of hashing. You should think not of cryptographic hashing, but more general hashing. Okay, so I want to show fingerprinting as you are going to find it in the complexity book at Barak in a work. So I'm not just going to tell you what it is. I'm going to try and show you what it does. So imagine this problem. You have a polynomial f over here over the integers. It's a multivariate polynomial. And imagine that I give you a circuit that computes f. So why aren't I giving you, and I ask you, is f the zero polynomial? So why aren't I giving you f? Because maybe, f is of exponential degree, for example, but I can encode this very complicated object into a circuit of polynomial size. Yes, so this is one intuition. So there's a circuit, and the circuit represents a polynomial. The circuit is a polynomial size. All right, so a tool we're going to use, so we want to check if it's the zero poly, and of course we cannot try, it's madness, and you can't try over everything. So we're going to use probabilistic checking, and our core tool is going to be generalized form of Schwarze pool. Consider a subset of an integer s, and then for any non-zero polynomial, so if you sample n random integers from this set s, then the evaluation over those numbers is going to be non-zero with the least probability 1 minus degree of f divided by the size of s. So if f doesn't have too large of degree and s is large enough, you're going to get a good probability here. Cool. So it's pretty straightforward what we do next. We pick some m that's going to be large enough. And then we sample all these guys from there, and we return, we say, okay, so if we evaluate f and we get 0, then we can sort of conclude, oh, that was maybe the zero polynomial. Otherwise, we say no, non-zero. Okay, so what is m we're going to pick, right? Let's reason about that. So, of course, we want to, this is complexity theory, we want to just say polynomial. How big is this m? Okay, let's do an observation. The fact that the circuit has polynomial size, well, tells us that potentially, that as we said earlier, the degree of f, the total, this is the total degree, by the way, could be exponential. So so imagine that you have all these multiplication gates, and every layer, every time you have a new multiplication, you're doubling the degree, of course. So if you have polynomial depth, which you have because you have polynomial size, you're getting 2 to the poly degree. There's a lot, but we can handle that. And then for constant error, which you can improve with repetition, you can get something like take m approximately 100 times the degree of f. And so you're handling something of logarithm of m bits, which is polynomial. And so you're happy. Are we done? Not quite. There's a catch. I mean, we're using, so we reduced the original problem, 0 polynomial, to checking, basically using Schwarzschild on something reasonable. But this is not polytime yet. And here's the reason. So the problem is not with how we're sampling things. So we're sampling each of the RIs small enough, so it's going to be a poly-sized thing. All good. But then look at what happens. So look at the circuit on the right. The problem is the evaluation of f. So when you plug in the R1, Rn, everything is fine. Then you start computing the circuit, and then what happens? So every time you have a multiplication, the size of the integer may be doubling, and then doubling, and doubling, and so on and so forth. You're doing this a polynomial number of times. You're going to get something exponentially sized pretty soon. So if you're handling the intermediate wires, you're not a polynomial time machine anymore. And the problem has to do with that we're working over the integers, of course. And here comes fingerprinting. So what are we going to do? So this is our choice of m. We do the thing that's not so surprising in a sense. So we pick a random number. We can pick a random prime that's large enough. Random prime q. And instead of evaluating f over the integers, after we sample R1, Rn, we compute the whole thing mod q. So basically, we're doing modular reduction all the time, meaning that we're never going to go beyond L bits, and we're going to be happy. That's it. So far, so good. I'm going to tell you something about the analysis. And if you, by the way, if you're confused or bored about anything here, happy news. As soon as this slide is over, all you need to get from this is that you do modular reduction through a random prime, and all you need to ask yourself, and I'm going to try and play with that, how do we use that for efficient SNARKs? Okay, so don't worry too much if you're bored or confused. But if you have a question, this is a good time. Okay.
What is the bit size of the prime?
Yes. Yeah, we're about to see. Yes, no, good question. Exactly. So what we need to check is that. Then, yes.
Yeah, and you said it's going to be a random prime, but how are you going to generate how is it generated?
Right. So I envision sampling L random bits and checking their prime, testing them, and then by the prime number theorem, you should get that in good time. But yes.
Okay, but it's not generated before everything is generated at a certain step.
It generated what?
Is it Q different every time, or it's generated after that we sample the random numbers? Or?
Yes, it's generated. You can see that as generated after sampling the random numbers. This is not an adversarial setting, so it matters relatively. But yes, you do that once, and then you use that Q for the whole evaluation of the circuit.
Okay.
I guess I have a kind of a continuation of this question. Tell me if it's too early in the slides, but usually we were thinking about the regular field SNARKs in terms of running over a certain elliptic curve, right? And you can't really, it would be probably very inconvenient to sample a new curve.
That's right. Yes.
So right. I guess, so you will explain that a bit, right?
Yes, but that's a very good point. Yes. exactly.
Because I guess that's kind of what the question is. I mean, if we don't if we want to commit to something, we need a group, and yeah, Q needs to be like we need a group here somewhere. I feel.
Yeah, maybe exactly. I mean, that's one of the challenges. But yeah, and we're gonna sort of I'll tell you, we will try to bypass these problems. Those problems are going to be in our way, but we'll try to bypass them. And then somebody else could try and go ahead first in some future work. So the rest of the slide, I mean, I'm going to release these slides somewhere, but let's make it quick so we're on time. It's just to convince you that this works, so that we need to check that, soundness still works. If I'm evaluating this, I'm checking the right thing, and Q is of the right size. And spoiler alert, Q is going to be of the right size because reasons. It's going to be polynomial here. But then the actual analysis is it's not complicated, but it just requires more time and more focus. But we can see easily that, if we do this, we're sort of keeping complete correctness in a sense. So if that was the zero polynomial, or the test we were doing was giving us 0, then when we do the mod Q, this is still 0. And then if we were going to be different than 0, then, and this is the analysis I'm skipping, then this is going to give you a false result only under a certain event, which is when Q, this randomly sampled prime, happens to divide the thing, the evaluation output, and then you can show easily with a couple observations that this is not a problem. Nice. But fingerprinting is this. So when we talk about fingerprinting, I'm going to talk about the sampling of this Q. And then the fact that we're reducing this complicated object in a vague sense, right? So the evaluation of the polynomial to something Q. Fine. But then let's talk about how we use that for our setting, right? So this was a completely different thing. Let's talk about non-deterministic computations over the integers. All right, and here's an attempt to a template. So let's try, I'm going to give you what may be reasonable to do. Let's establish some notation. There is a prover and a verifier, of course. The prover is a witness. The verifier, so we have some computation C. It doesn't matter how it's represented, just that something is a witness if C of W is 0. And the verifier may be some type, it doesn't matter what for now, some type of verifier key for that computation, okay? Some pre-processing or so. So if we find, we need to find a way of computing it, but it doesn't matter. So we're going to try and exploit some intuitions. We'll try and leverage them, and we're going to fail. So we want, of course, we have this computation C, we have fingerprinting. Let us fingerprint the computation now. And SNARKs usually work modulus finite modulo Q. Let's try and use a SNARK for mod Q, where Q is this random primary sample. And Misha already anticipated some of the challenges there. There are more. There are even more. Okay, so here's the template. Let me try and unpack it for you. So forget about the color coding for now. Just ignore it. But it's easy to figure out. Yellow is, hopefully you can all see the colors. Yellow is integers, and it's pre-sampling of Q, and everything that's pinkish is after or at the sampling of Q. So, okay, the first thing the prover does is it commits to the witness in some way. It sends me a commitment to the witness. Then, okay, the witness is fixed. I sample a large enough prime. This is just a set of primes of lambda bits. I send it, and then we do this fingerprinting. We reduce this computation to something mod Q. What the hell does it mean? We don't know yet, and that's the problem, right? Let's ignore all that. So we reduce the thing, and then we use some SNARK that can work modulo Q. We plug in Q, and we use it to do for the following statement. I know witness W such that this computation mod Q gives checks, so that's a witness mod Q, whatever that means, and W is committed in the original CM. So I as a verifier can get this proof pi and check it. Nice, but we're far from being done. There's many challenges here. So what is the SNARK we're using that? And what properties are necessary for any SNARK to put there? What does it mean to reduce the computation mod Q? And why is it sound? Why should this work, even if we define that? And look at this. I mean, the third point, you can see this part over here. So when I'm generating this proof pi here, I'm talking about two very different types of object. I have a commitment CM over the witness, over the integers, because W is committed as such here. But I'm also dealing with a computation mode Q. So this must be a very strong SNARK to be able to do that. Okay, let's look at, I'm going to anticipate some of the answers or how we're going to tackle them. But here we go. So what are the challenges in instantiating the SNARK? Well, Q is random. And we know the SNARKs usually use, lots of cryptographic primitives. So whatever Q we're sampling, it better give us discrete log friendliness and or fast Fourier transformation friendliness and or some multiplicative subgroup or additive subgroup with certain properties where you can use a univariate sum check. Good luck with that. So if any of your proof system you were trying to use that, it's hard to plug in here. And also, you may be thinking of field agnostic SNARKs here in polynomial commitments, but this is not going to help you. And the reason is that often these type of primitives, they have, you need to, when you're committing, for example, here on the left, you need to know what Q is. So Q is unknown for too long because it's going to appear only later. When you're committing the witness, it's too early. And then the verifier key, of course, that you need to compute, you need to be able to preprocess and therefore usually commit to the relation, which is on the integers, before you know Q. And then, so field agnostic SNARKs are not going to give you that. So these are things you cannot use, but there are things you can use. And so schemes based on multilinear extensions, actually GKR flavored techniques, Spartan, Hyperplonk, they seem to be good candidates because all of these things are more, sum check works, multilinear extensions work, and so on and so forth. Sum check works over the field, I'm sorry, but multilinear extensions, they keep their properties. And we're going to have time to look in, to go to look at this directly, but this is an intuition. And then what does it mean to reduce here? So let's do this. So assume that C, this sum computation, is what I'm calling it ZR1CS, which is just an R1CS. So a bunch of vectors AI, BI, CI that are sparse, and they have, instead of field elements, they have integers. So, okay, so I have all these systems of equations now, and that's my R1CS. And guess what? It's very straightforward to reduce it. So to fingerprint that. So when I go mod Q, what do? I just do the whole arithmetic mod Q. So you give me W, and the computation mod Q is just, let me check the system of equations over FQ. Yeah, makes sense? So it makes the thing we're doing. Okay. And then, of course, if this is correct, if the thing was a witness, it stays a witness. And then you can prove, we're not going to do that here, but you can prove that if you plug in a witness in this fingerprinted relation with low probability, it's going to give you, sorry, if you plug in a non-witness with low probability, it's going to give you a yes. And the part of the intuition comes from the degree 2 of this. And the degree shows up in Schwarzschild and so on and so forth. Okay, so this is a flavor of how we're going to answer some of these questions. But in general, this template is just to give you an idea. But to see the whole answer, I need to do this. I need to say, just forget about this. And so that was just to give you a flavor. But the actual framework works differently. So the actual framework we have, so we asked ourselves, how do you capture general construction? And there is one recipe that's sort of standard. It's not perfectly standard, but it's algebraic holographic proofs plus polynomial commitment, okay? And variants of that. So you have an information theoretic object and a polynomial commitment. And so that's what we're going to look at. And so all this thing I just showed you is going to be implicitly captured here. And then I probably will speed up things. So let's see what happens because we have 5 minutes left. Cool. So let's do this very quickly. I'm going to assume you know what an algebraic holographic proofs or polynomial P's and so on and so forth is. And it's an idealized protocol where the prover in a field that's pre-known sends oracle polynomial. So the verifier receives an oracle to a polynomial, sends a challenge, receives another, and then at the end it just asserts certain equations. So it can access evaluations of these polynomials over random points and then check this. Fine. All the arithmetic is mod Q. So, and how do we compile these things? So an HP is not a protocol yet, a real protocol is an abstraction of sort. We can make it real, in some sense, adding a polynomial commitment. So polynomial commitments bring these oracle polynomial to the real world by committing to them. Instead of, I take P1 and I commit to it and I send it, you send me the challenge, and then there's a P2 and then I commit to it. And then I, as a verifier, I have commitments, and I can ask you for evaluation points. The evaluation points being rho and sigma. You can give me the outputs, A1, A2, B1, B2. I can plug them in my equations. Give me proofs. I check the proofs. Everybody's happy if they'll check. Okay, so if this is the recipe, how do we adapt it? Well, let's adapt HPs first. And so we move from, in our framework, we move from HPs to HPs over integers with modular remainder queries. So for short, mod HPs. And the problem we have here is that we need to get rid of fields, at least at the beginning. And then we need to sample the prime. And that's exactly what we do. So you can imagine that there is no field at the beginning. The witness is a vector of integers. And then the prover can send me one or more or whatever oracle polynomials, 2 integers. And then the verifier samples a random prime. And then we keep going and we keep going. Now the field is specified. Now we can keep working as we are known. But what happens at equation checking time? So, you have, what are the oracles I have? I have Z, I have P1, I have P2. But Z is over the integers. Am I going to check this thing over the integers? No. A mod HP is something that forces the verifier to check mod Q. So everything is going to happen mod Q there. Right? And then this is important. This is sort of how fingerprinting is embedded in this. And if this is confusing you, don't worry. It's easy to see either from the paper or hopefully from these slides more slowly, but it just means take HPs, think about all the design challenges that come from thinking about fingerprinting and apply fingerprinting to them. The cool feature here is that we never evaluate anything over Z. And that means that everything is arithmetic of lambda size and that the first milestone towards full succinctness. Okay, I'm gonna speed up even more here. And okay, so we have a variant of polynomial commitments that reflects this. This is standard polynomial commitment, so you extract the polynomial. But we need to apply fingerprinting, so there's a little bit of messiness here. So imagine we have a polynomial commitment notion that we can use to compile that. And there's things to say about knowledge soundness, that there are design challenges there, how to make it simple. Okay, all right. I'm just going to say, how do we instantiate our mod HP? We have a framework, right? So we want to think about how to instantiate that. And we look at Spartan, and you can change Spartan. Thank you, folks. You can change Spartan, and I'm going to be off of 1 minute probably, 1 or 2, but we're wrapping up. We choose Spartan, and we see that we can just mull it a little bit and introduce this sampling of the prime. And this is great. It's very simple. What's easy is to prove that it satisfies a certain notion of knowledge soundness, which I haven't been able to talk to. But this is what's hard. What's really hard, nonetheless, is making the verifier not pay for the oracle access to polynomials that depends on the matrices of their R1CS. One of the key contributions of Spartan is exactly that, is how to go from a dense polynomial commitment to a sparse polynomial commitment. And making those techniques work require lots of work on our framework. We need to introduce delayed input stuff. I'm not going to get into that. I just want to mention that the techniques they're sort of a lens, they're sort of a bunch of recipes for functional commitments that have this fingerprinting flavor. And we have an formalize that so generally, but I see that as a low-hanging fruit. Fine. Let's keep going. So I'm just going to say, how do we instantiate our polynomial commitment? Well, the techniques are sort of dark flavor, so groups on an order, and none of the previous works gives us exactly what we want. There are a bunch of challenges, and so we need to add a few building blocks in the end. It's an open problem on how to adapt them better. And we're at the final slide, actually. So wrapping up, we saw SNARKs for Z, SNARKs for, we have full succinctness, so we have no linear dependence in the bit size of the largest element of the witness or number of witnesses. There's a general framework and a concrete construction. We're looking forward to look at ZK, which is a non-trivial problem. And then we're already looking at different polynomial commitments and different techniques to achieve that. Because while the mod HP is very efficient, the one we have, I cannot say the same for the polynomial commitments. It's unclear for which setting this is going to be the state of the art from the final fields work. But I think it's not going to, we're not that far from getting something very efficient. And of course, you can try different HPs to apply this framework to different HPs. A low-hanging fruit is hyperplonk, of course. We haven't done that, but there could be other proof systems out there. Thank you for your attention.
Okay, thank you a lot, Matteo. And I'm sorry that it had to be a bit rushed towards the end.
That's all right.
I will take a liberty to suggest that we will stay for some time for the questions, and if people want to ask questions, they need to run. They better do it first, and then we can maybe prolong it by 5-10 minutes if people are comfortable with that. If we have questions.
I'm afraid I'm going to be the party pooper. I need to leave in a couple of minutes, but we can take a couple.
Okay, sure. Sorry, I assumed.
No, that's all right. That's right. I would have loved to. Unfortunately,
okay. I have too many questions. I can ask them offline, so maybe I'll. Yeah. Does someone have questions to Matteo?
Okay, Misha, maybe it's...
Yes, I do have a lot. I'll just pick a random one. I was kind of wondering, so I wanted to get a bit deeper into the polynomial commitment scheme because that looked very weird to me. So there's a polynomial commitment that needs to work with arbitrary Q, but it's still in the group, right? So what is the G here? G belongs to what?
Oh, yeah. It's a generator it's a group element in the...
in the what?
In a group of unknown order. It could be an RSA group, or it could be,
So you're assuming either strong RSA for a publicly known parameter, or you're assuming a class group here?
I'm either assuming what, I'm sorry?
You're either assuming a strong RSA on the public modulus, so you have some kind of public setup, or you're assuming an existence of a class group.
Yes.
So you do have a proper integer commitment that is not the public verifier integer commitment.
I'm sorry, I didn't get the part about publicly verifiable.
Well, yeah, you need to have a publicly known group with public parameters that is of a known order. Yeah, okay. It's usually not hard to achieve.
Which is fixed once and for all. Yes, that just to make clear.
Okay. And you can commit that by raising G to the evaluation of F. I had a privilege to take a look at the paper.
And that's, by the way, the Q here. This is what happens when you have this. You make slides this way. If you make a mistake, you pay for it, and so the Q. I shouldn't have used Q there, but the Q is not the Q we sample. It's an
okay. That's just a different evaluation point. Okay. Yeah. Okay, sounds good. Maybe another question I wanted to ask is that what is the kind of what can you see? I mean, you had a lot of motivation, but what can you see as the potential, maybe the most useful application of them all? What are the computations that you actually want to run over the integers quite often? Maybe something lattice related.
No, yeah. So I think, okay. So here's a quick answer. I think RSA is very exciting and RSA flavor stuff because I think we're close to coming up with something to speed them up. But two caveats. RSA stuff is interesting trade-offs for, say, accumulators, but some of the metrics there are not great. I mean, if you're doing RSA computations, then this slows things down sometimes. So, but then you can have a proof system on top of those that's going to be good, but maybe it's not going to be the most impactful thing. So I've high confidence there, but lower impact, but higher impact and lower confidence because I don't know how it's going to work is the machine learning stuff. I think I played with this problem for a week, floating point arithmetic and such, and I haven't found still a way to do that. But someone smarter than me or me less sleep deprived than me might make me to do something in the future. Yeah.
Okay, can I also like extend the query question a bit? What did you think about anything that is post-quantum secure? So if I understand correctly, correct me if I'm wrong, class groups are assumed to be post-quantum secure.
Yeah.
I don't really know how they work underneath. So what do you need to implement like a class group operation? But are these operations require like integer operations? Like for example, if you have some kind of accumulator scheme on class groups, can this be used to prove something about the accumulation results?
If you have, what's the building block you assume? If you have what? I
want to think about something like RSA groups, but post-quantum secure, because I don't really have a strong feel that RSA groups will be used in 10 years.
Yeah.
So do you see that we can build some kind of class group accumulators and prove statements about accumulation over class groups?
Yeah. No, the answer is yes. So the problem with that is just efficiency, I think. I'm not acquainted with the last 5 years in terms of improvements on class groups, but 5-ish years ago or less, they weren't great. I think they were a nice theoretical feasibility result. So, but yes, the techniques should be compatible. Yes.
Okay, maybe something lattice related as well can be quite good if you have like really, really big vectors, but
I should think about that. Yeah.
This work is completely the opposite of what people are trying to do, right? With the most hyped area where they try to reduce everything to 32 bits. So I think there needs to be like, I can clearly see there are good applications, but I guess like what is the most sought for application, I think is a question that might be good to have a separate answer for what people like would love the most.
Yeah. I think maybe I completely agree. I think there's still fuzziness there. Now I want to say maybe I should run. I want to just go back to, yes, let's see if it's feasible. Well, you can contact me here. That's what I want to say. Yes, exactly. Oh, there's no my email here, but you can find my website and Matthias's and the print. So feel free to write to me.
Well, thank you a lot, then, and thanks everyone, and thanks again, Matteo, for giving a great talk. Yes.